Hello everyone. In this lecture we talk about the quantum mechanical model of the hydrogen atom. The Bohr theory of the hydrogen atom, although not wrong, was also not quite right. A new approach to the nature of the hydrogen atom was necessary. When de Broglie introduced his matter wave in 1924 to describe particles, it became necessary to develop a technique to find these matter waves mathematically. Then Erwin Schrödinger, 1887 to 1961, an Austrian physicist, developed a new equation to describe these matter waves. This new equation is called the Schrödinger wave equation. In fact, the Schrödinger wave equation is to the quantum mechanics what Newton's second law is to the classical mechanics. And the Newton's second law can be derived as a special case of the Schrödinger wave equation. The solution of the wave equation is a wave function psi. For the quantum mechanical model of the hydrogen atom, the Schrödinger wave equation is applied to the hydrogen atom. And it was found that it was necessary to have three quantum numbers to describe the electron in the hydrogen atom in this model, whereas the Bohr theory has required only one. The three quantum numbers are: the first one is the principal quantum number, n, which is the same as that used in the Bohr theory. And the second one is the orbital quantum number, L, and the third one is the magnetic quantum number, m sub L. These quantum numbers are not completely independent, because n can take on any value given by n equal to 1, 2, 3, etc., whereas L, the orbital quantum number, can only take on the values L is equal to 0, 1, 2, 3 to n minus 1. Thus, L is limited to the values of the up to n minus 1. The magnetic quantum number m sub L only can take on only the values given by m sub L is equal to 0, plus minus 1, plus minus 2, 2, plus minus L. Hence, m sub L is limited to values up to minus plus 1 L. Let us now see a physical interpretation for each of these quantum numbers. The principal quantum number, n, at first, plays the same role in the quantum mechanical model of the hydrogen atom as it did in the Bohr theory, in that it quantizes the possible energy of the electron in a particular orbit. The solution of the Schrödinger equation for the allowed energy values is E sub n is equal to minus k square E2 is 4m over 2 h bar square multiplied by 1n over n square, which we see had the same energy values as given by the Bohr theory in equation E sub n is equal to minus mk square E is 4 over 2n square h bar square. They have the same form. Therefore, n has the same role in the quantum mechanical model and the Bohr theory. In the Bohr theory, the angular momentum of the electron was quantized according to the relation L equal to nh bar, where L is angular momentum. The solution of Schrödinger wave equation gives for the angular momentum the relation L angular momentum is equal to root square over L orbital quantum number multiplied by L plus 1 h bar. Therefore, L, this is orbital quantum number, not the angular momentum, sorry. L is equal to 0, 1, 2, 3, 2, n minus 1. We have an example about the angular momentum of an electron in a quantum mechanical model of the hydrogen atom. Say that determine the angular momentum of an electron in the hydrogen atom for the orbital quantum numbers of in A, L equal to 0, in B L equal to 1, in C, orbital quantum number L equal to 2, and in D, L equal to 3. To solve this problem, we say that angular momentum is L is equal to root square over of L multiplied by L plus 1 h bar. In A, we substitute the value of orbital quantum number L is equal to 0 in this equation. Then we get angular momentum L is equal to root square of 0 multiplied by 0 plus 1 h bar, and it equal to 0. Thus, for the L equal to 0 state, the angular momentum of the electron is 0. This is a very different case than anything found in the classical physics. For an orbiting electron, there must be some angular momentum. And yet for the L equal to 0 state, we get L equal to 0. Thus, the model of the atom with the electron orbiting the nucleus must now be considered questionable. We still speak of orbits, but they are apparently not the same simple concept used in the classical physics. In the second case, when we have L equal to 1, orbital quantum number equal to 1, by substituting this value in this equation of the angular momentum, we get L equal to root square of L plus L multiplied by L plus 1 h bar, and we get its value is equal to 1.41 h bar. In the third case, L equal to 2, the orbital quantum number L equal to 2, then the angular momentum is equal to 2.449 h bar. For the last case, when L equal to 3, then angular momentum is equal to root square of 3 multiplied by 3 plus 1 h bar, and it's equal to 3.464 h bar. Note that in the Bohr theory, the angular momentum was a whole number of h bar. But in here, in the quantum mechanical treatment, the angular momentum is no longer a whole multiple of h bar. As we see, in the second case, equal to 1.41 h bar, in the third case, 2.44 h bar, and so on. It's not a whole multiple of h bar. In this table, we show the angular momentum and the orbital quantum numbers and its angular momentum and the symbol of the state. For example, if we have L orbital quantum number is equal to 0, we have the one value of the angular momentum, which is equal to 0, and this state is denoted by S, and it's called sharp. And in the second case, when L equal to 1, we have angular momentum is equal to root square of 2 h bar, and this shell denoted by P, and it's called principal, and so on, also about L equal to 2, 3, 4, 5. We have that there are different values of angular momentum, and they are denoted by the subshell denoted by D, F, G, and H. And in this table we have atomic status in the hydrogen atom. We have the principal quantum number N and the orbital quantum number L. For n equal to 1, we have one value of L, which is L equal to 0, because we have L values from 0 to n minus 1, n minus 1, n minus 1 equal to 1 minus 1, and equal to 0. We have a L equal to 0, and this state called 1s. For n equal to 2, then we have two values of orbital quantum number, which they are L equal to 1 and equal to 0. They called 2s and 2p. And so about another values of n. For example, if we have n equal to 6, we have 6 values of orbital quantum number. They are L equal to 0, which is called 6s, and L equal to 1, 6p, and L equal to 2, 6d, and L equal to 3, 6f, and 6g, and 6h.